In episode 79, titled Bias-Variance Tradeoff, Diagnosing Overfitting and Underfitting by Symptoms, the goal is to use bias and variance to explain model behavior quickly because the exam often gives you just a few clues and expects you to name the failure mode and the right fix without hesitation. Bias and variance are not academic labels. They are a practical shorthand for why a model is consistently wrong in a predictable way or unpredictably wrong depending on the sample it learned from. In real systems, this trade-off also guides how you spend effort because you do not fix a high bias model by tuning tiny hyperparameters, and you do not fix a high variance model by adding even more flexibility. The point is to diagnose first, then change the right lever, because the symptoms tell you what kind of problem you have. When you can name bias and variance correctly, you can also communicate model risk more clearly, explaining whether the model is too rigid or too fragile. This is one of the fastest decision tools you can use under exam time pressure. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Bias is systematic error caused by overly simple assumptions, meaning the model is missing real structure because it cannot represent it. A high bias model tends to make the same kinds of mistakes repeatedly, such as failing to capture nonlinear relationships, ignoring important interactions, or treating distinct segments as if they follow one universal rule. Bias is not about randomness. It is about a mismatch between the model's representational capacity and the true complexity of the relationship you are trying to learn. In a bias-heavy setting, even if you give the model more data, it will still fail in the same way, because the model family does not have the right shape to fit the underlying pattern. The exam expects you to recognize bias as an assumption problem, because the fix usually involves changing representation, features, or model flexibility rather than simply training longer. Bias can also be induced by poor feature design, where the features do not capture the mechanisms, making even a flexible model behave as if it were simple. When you define bias clearly, you are describing a model that misses broadly and consistently. Variance is sensitivity to training data fluctuations, meaning the model's behavior changes substantially when you train it on different samples because it is fitting noise along with signal. High variance appears when the model has too much flexibility relative to the amount of evidence, so it can memorize idiosyncrasies of the training set that do not repeat in new data. A high variance model often looks impressive on training data because it can fit the quirks well, but it performs poorly and inconsistently on validation because those quirks do not generalize. Variance is not about the model being bad, it is about the model being too responsive to the specific sample it saw, which makes it fragile in the face of natural variability. The exam expects you to associate variance with instability, such as coefficients that swing wildly, feature importance that changes across runs, or performance that varies greatly across splits. When you define variance clearly, you are describing a model that swings wildly across samples rather than learning stable structure. A reliable symptom of high bias is poor performance on both training and validation because the model is too simple to fit even the data it has seen. If training loss is high and does not drop much, and validation loss is similarly high, that suggests the model cannot capture the structure needed to predict well. High bias is also suggested when residuals show systematic patterns like curvature or consistent segment errors even after reasonable tuning, because those patterns indicate structural mismatch. The exam often frames this as the model performs poorly everywhere, or increasing training time does not help, which should trigger a high bias diagnosis. Another cue is when adding small tweaks does not change the errors because the limitation is not settings, it is capacity or representation. In practice, a high bias model can look calm and consistent, but consistently wrong, which is why the misses broadly language fits. When you see broadly poor performance, you should suspect bias before you suspect fine-tuning issues. A reliable symptom of high variance is great training performance but weak validation performance, meaning the model fits training patterns well but fails to generalize. This often shows up as training accuracy climbing steadily while validation accuracy plateaus or declines, or as training loss dropping while validation loss stops improving and may even rise. High variance is also suggested by instability across different random splits or time windows, where performance varies a lot and it is hard to reproduce the same result twice. The exam often describes this as the model performs very well on training data but poorly on new data, which is the classic overfitting clue. Another variance clue is a model that changes its explanations frequently, such as coefficients flipping sign or top drivers changing, because the model is chasing different noise patterns in different samples. In practice, high variance is the fragile model problem. It looks great in the environment it memorized and unreliable elsewhere. When you see a large generalization gap, variance should be your first suspect. Reducing bias usually requires increasing the model's ability to capture structure, either by adding better features or by using a more flexible model family. Better features often mean representing the mechanism more directly, such as adding rates, recency, interactions, or transforms that linearize nonlinear relationships. More flexible models can capture nonlinearities and conditional rules that a simple linear form cannot, such as tree-based models for threshold-heavy patterns. The exam expects you to choose these remedies when the model is underfitting, because an underfit model needs more representational power, not more constraints. However, adding flexibility without evidence can create variance, so you still validate carefully, but the direction of change is toward capturing structure rather than toward simplifying. Reducing bias can also involve revisiting target definition if the target is too noisy or poorly aligned, because no model can learn clear structure from an incoherent target. When you reduce bias correctly, you should see training performance improve, and ideally, validation performance improve as well if you added real structure rather than noise. Reducing variance usually requires making the model less sensitive to sample quirks, either by applying regularization, adding more data, or using a simpler model. Regularization discourages overly complex parameter settings, forcing the model to focus on stable patterns rather than on rare coincidences. More data helps because it provides more evidence for true relationships and averages out noise, reducing the chance that the model mistakes a coincidence for a rule. Simpler models reduce degrees of freedom, which limits memorization capacity and can improve generalization when signal is modest. The exam expects you to choose these remedies when the model is overfitting, because an overfit model needs constraint and evidence, not additional flexibility. Another variance reducer is feature pruning or grouping, especially when high-dimensional sparse features invite memorization, because removing low support features reduces the opportunity to fit noise. When you reduce variance correctly, the training score may drop slightly, but validation performance should become better and more stable, which is the trade-off you want. Scenario cues are how you diagnose quickly, and the exam often gives you phrases like unstable results, consistent misses, or great in training, poor in testing to signal which side of the trade-off you are on. Unstable results across folds or time windows indicate variance because the model is responding too strongly to which examples it sees. Consistent misses across regimes indicate bias because the model is missing a systematic relationship that does not change with sampling. If a scenario mentions high-dimensional features, rare categories, or complex interactions with small sample size, you should lean toward a variance risk diagnosis unless evidence shows the model is too simple. If a scenario mentions residual curvature, threshold effects, or a linear model used on a clearly nonlinear process, you should lean toward a bias risk diagnosis. The exam also tests whether you will choose the wrong remedy, such as adding complexity when variance is the problem, or adding regularization when bias is the problem. So diagnosis must come before prescription. When you practice cue recognition, you can answer quickly without guessing. Learning curves provide a conceptual tool for seeing data needs and model capacity, and you do not need to plot them to understand the logic. A learning curve describes how performance changes as you add more training data, and it reveals whether the model is limited by bias or variance. In a high bias setting, both training and validation performance are poor and close together, and adding more data does not improve much because the model cannot use additional evidence effectively. In a high variance setting, training performance is high while validation is lower, and adding more data often improves validation and reduces the gap because more evidence constrains memorization. The exam may describe that more data improved validation significantly, which suggests variance was a major issue, or that more data did not help, which suggests bias or target noise. Learning curve intuition also helps you decide whether it is worth investing in more data collection versus investing in representation changes, which is a real-world trade-off. When you think in learning curves, you are aligning your next step to what is likely to help. A common mistake is adding complexity when validation performance stays flat, because flat validation is a sign that complexity is not capturing stable structure, and it often means you are just increasing variance. If validation does not improve with added complexity, the issue may be weak signal, noisy labels, misdefined targets, or missing key drivers, and these are upstream problems that complexity cannot solve. The exam expects you to resist the urge to keep escalating model sophistication in that situation because it leads to overfitting and wasted effort. A better response is to revisit data quality, feature meaning, and enrichment options, and to use controlled experiments rather than broad changes. Flat validation is also a cue to check whether your evaluation design is appropriate, because leakage or poor splitting can hide true behavior. But assuming evaluation is sound, flat validation suggests you should stop adding complexity. When you avoid unnecessary complexity, you protect maintainability and reduce operational risk. Balancing bias and variance is not about perfect theory. It is about cost, interpretability, and deployment needs, because the best point on the trade-off depends on what errors cost and what constraints exist. In high-stakes systems, you may accept a slightly higher bias if it buys stability, interpretability, and safer deployment, especially when decision-makers require clear explanations. In competitive environments where small improvements yield large economic value, you may accept more complexity and manage variance with careful validation, regularization, and monitoring. Cost matters because high variance models often require more data and more retraining to stay stable, while high bias models may require feature engineering and more sophisticated modeling to capture structure. Deployment needs matter because a complex model may be hard to serve under latency constraints, making a simpler, slightly biased model preferable. The exam expects you to reason that bias and variance are trade-offs, not moral judgments, and that the correct choice depends on constraints. When you discuss trade-offs this way, you sound like a practitioner who designs systems, not like a student reciting definitions. Communicating the bias-variance trade-off should be framed as stability versus flexibility, not good versus bad, because stakeholders understand those operational consequences better than abstract statistical terms. High bias is a model that is too rigid, which makes it stable but systematically wrong in certain patterns, while high variance is a model that is too flexible, which makes it fit training well but behave unpredictably on new cases. This language helps leaders understand why a model can look great in development and disappoint in production, and it supports the case for guardrails, monitoring, and data investment. The exam often tests whether you can explain these concepts simply, because real decisions depend on clarity. Framing the trade-off as stability versus flexibility also supports model selection decisions, because the organization must choose how much complexity it can manage for how much improvement. When you communicate this cleanly, you increase trust because you are explaining behavior in operational terms rather than hiding behind math. A helpful anchor memory is bias misses broadly. Variance swings wildly across samples. Misses broadly means errors are consistent across training and validation, and the model fails to capture structure. While swings wildly means results change with the sample, and the model is fragile. This anchor is valuable under exam pressure because it converts abstract terms into observable symptoms you can map to scenario cues quickly. It also keeps the remedy aligned. Broad misses point to adding structure, and wild swings point to constraining complexity and adding evidence. The anchor prevents a common error where people treat any poor performance as a sign to add complexity, when poor performance could be bias or could be weak signal and noise. When you use the anchor, you can diagnose and respond in a disciplined way. To conclude episode 79, diagnose one case and then choose one corrective action, because the exam often requires this exact move. If a scenario says a model has very high training accuracy, but validation performance is barely better than baseline and changes significantly across different validation splits, that is a high variance pattern. A corrective action is to increase regularization or simplify the model, and to reduce feature dimensionality by removing low support and redundant features, then reevaluate using the same validation design to confirm the generalization gap shrinks. If instead a scenario says both training and validation performance are poor and residuals show clear curvature, that would be a high bias pattern, and the corrective action would be to add a transform or choose a more flexible model family, then validate that both training fit and held-out performance improve. The key is that the corrective action follows the diagnosis, not the other way around, and it is validated with honest, held-out evidence. That is the bias-variance trade-off in practice. Use symptoms to choose the right lever. Then test whether the change improves stability and outcomes under real constraints. Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.